Welcome back to our discussion on aqueous reactions. In the last series of videos, you saw this list of types of reactions that can occur when aqueous solutions are mixed together. Number one, we covered when talking about solubility and the formation of a precipitate, which is an insoluble solid. The second type of reaction that can happen is the formation of a gas. And when a gas forms, we usually can visually see it because we see the bubbling and fizzing. We will see a real quick example of that in the acid-base section. So in this video here, we're going to talk about acid and base neutralizations. So before we can talk about exactly what an acid-base neutralization is, we need to focus on what an acid is and what a base is. So acids are substances that will ionize or dissociate in water. When you dissolve them, they go into ion form. This causes an increase in hydrogen ions. We're going to see an increased concentration of H pluses in solution form. These H ions are bare protons. There are no electrons around them. And the acids are usually considered proton donors. So they give H pluses when they dissolve. Two acids that we will come in contact with the most are monoprotic acids and diprotic acids. Monoprotic acids, when they dissolve in water, they will produce one hydrogen ion per molecule. So when they dissociate, just one H plus is given off. Things like hydrochloric acid or nitric acid, when they ionize, one H plus forms. In diprotic acids, such as sulfuric acid here, H2SO4, the ionization will occur in two steps. First, we will see the ionization of one H plus off of the sulfuric acid compound. So we're going to see sulfuric acid break up into H plus and HSO4 minus. The second step will be the HSO4 minus ion dissociating into another H plus and the sulfate ion. This does not occur completely. Some of the molecules will, or some of the ions will stay as the HSO4, and others will break up into the second hydrogen and sulfate ion. When we talk about the strength of sulfuric acid, since it is a strong acid, we are looking at the first ionization. So we're looking at the first ionization equation here. What are bases? Well, they are substances that will increase the hydroxide ion when added to water. So the majority of bases will have an OH in them. An exception to that is NH3, which the common name is ammonia. It's important that you are able to interchange ammonia and its compound. So when I say ammonia in class, NH3 comes to mind. When it is added to water, it will take on a hydrogen ion, forming NH4 plus, and it leaves the OH negative or the hydroxide ion from the water in solution. So it is considered a weak electrolyte because only about 1% of ammonia will ionize. So only 1% will break up into ions. The rest will stay as NH3. So what's the difference between strong acids and strong bases? Well, strong acids and bases will ionize completely. They're strong electrolytes. Those that only partially break up into ions or partially ionize are considered weak acids and bases. So let's do a little wrap up on what strong and weak electrolytes are. If you're looking at an ionic compounds are strong electrolytes. They will always ionize completely. Molecular compounds, it depends on what it is. You need to think to yourself when you're looking at a molecular compound first, is it an acid? If it's an acid, it will be an electrolyte. Now, how do we know if it's a strong or weak electrolyte? Well, a strong acid is a strong electrolyte because it will completely ionize. A weak acid is a weak electrolyte because it only partially breaks up into its ions. Then you need to think if the molecular compound is NH3 or ammonia. If it is ammonia, then it's a weak electrolyte because ammonia ionizes about 1%. If it is not an acid or ammonia, it is probably a non-electrolyte. Here's a chart from your book, table 4.2. In this table, it lists the strong acids on the left and the strong bases on the right. You need to know the strong acids and strong bases. This was an assignment for you to do over the summer, memorize the strong acids and strong bases. Because if you know a strong acid, then any other acid's going to be weak. If you know the strong bases, any other base will be weak. Now the bottom table, table 4.3, also in your book, gives you a summary of electrolyte behavior. If you take a look, ionic compounds are always strong electrolytes. Molecular compounds, though, strong acids are electrolytes, weak acids and weak bases are weak electrolytes, and all other molecular compounds are non-electrolytes. Neutralization reactions are in a reaction between an acid and a base. Let's look at the properties of acids and bases before we actually get into the neutralization reactions. Acids will have a sour taste, where bases will have a bitter taste. Acids turn blue litmus paper red, where bases will turn red litmus paper blue. Acids like to react with metals, and bases will not. So just a few properties there. In a neutralization reaction, it is an acid being mixed and reacted with a base. The product of a neutralization reaction will not have any of the properties of an acid or a base. The acid reacts with a metal hydroxide to form a salt plus water. So when you mix an acid and a base, your products are always water, H2O, and then a salt based on the ions from the acid and the base. Here is hydrochloric acid, strong acid, mixing with sodium hydroxide, strong base. And when they mix, the H from the acid bonds with the OH from the base, forming water. And then the chlorine ion from the acid will bond with the sodium from the base, forming NaCl. If we wanted to write the ionic equation, break this all up and write it into an ionic equation, here's what we're going to see. In the reactant side, we're going to have sodium as an ion and hydroxide as an ion, hydrogen as an ion, and chlorine as an ion. But on the product side, we are going to see water stay as a compound because that L there indicates that it's a liquid. It is not an aqueous solution, so therefore it will not break up into ions. And then the sodium chloride will break up into positive sodium ions and negative chlorine ions. If we cancel out the spectator ions from both sides, we can see that a net ionic equation for a neutralization reaction is the hydrogen ion plus the hydroxide ion forming liquid water. It's very important. If you can recognize that it's a neutralization reaction occurring, you automatically know the net ionic equation, that it's hydrogen ion plus hydroxide ion equaling liquid water. Here we have potassium hydroxide mixing with sulfuric acid. What I would like you to do at this time is pause the video, write the full ionic equation, and then write the net ionic equation. But first, you're going to have to predict what your products will be. So go ahead and pause your video now and write this out in your notes. All right, welcome back. Hopefully, you were able to predict that we would form potassium sulfate and liquid water. Now, the potassium sulfate is our salt because it is a metal bond with a negative ion. So sulfate is a negative ion. We have a salt. And our liquid water is H2O. Always make sure you balance your equations before breaking them up. Here's your net ionic equation. The only thing staying as a compound is the water. And water can be written as H2O or HOH. Sometimes when dealing with acid bases, it's easier to break it up into HOH so you see the H and the OH. Cancel out spectator ions, and there's your net ionic equation. Sometimes when you have acids and bases react, you'll see that a gas forms. And this will happen because some bases are not all made up of OHs. We do have some bases that will have carbonate ions or will have sulfide ions in them. So when an acid and base forms in this instance, you're going to see a gas form during the neutralization. That's because bases that have carbonates or bicarbonates will react with an acid to form carbon dioxide gas. An example of this would be taking vinegar and baking soda. Vinegar is acetic acid and baking soda is sodium bicarbonate. So the gas that you see when you take vinegar and baking soda and mix them together is carbon dioxide gas. Acid spills and antacids. We usually use sodium bicarbonate or sodium carbonate to clean up acid spills in the lab. When we are dealing with acids, which we will a lot, I will usually have a liquid solution of sodium bicarbonate in wash bottles for you to spray on acid spills. And if you'd like to see a list of antacids, you can look on page 135 in your book. Antacids are medications that you can buy at any drugstore to help with heartburn or indigestion. And heartburn and indigestion occurs because you have a buildup of stomach acid in your stomach. And an antacid is a base. So when you take it, that base will interact with that stomach acid and bring the stomach acid down. What I want to do now is just real briefly talk about titrations. We'll have a unit later in the year that we talk about them in more detail. And a titration is used for determining the concentration of an unknown solution. So we use a second solution of known concentration. This is called the standard solution that undergoes a reaction with the unknown solution. Typically, we use this with acid-base reactions and a neutralization occurs. The point at which the two solutions are stoichiometrically equal is known as the equivalence point. And the reaction is complete and no excess reactant is present. How do we know when this occurs during a reaction? We use what is called indicators. So in acid-base reaction, these dyes or indicators are used. One that's very popular is phenolphthalein. It's colorless in acid solution, but as the solution starts to neutralize, and if it should go past being neutral and become basic or a base solution, it will turn pink. The end point is reached when a drop of the base remains pink. There is no acid for this drop to react with, and the solution is now basic. We will be doing labs with titrations, and we will also be doing a number of calculations with titrations. That is the end of this video, and our next video will cover oxidation and reduction reactions.